All right, we're going to look at an example from MyOpenMath homework for section 9.1. This is for hypothesis testing and also for confidence interval for two sample proportions. So here, I'll go ahead and read the question. We have ASD, which is autism spectrum disorder, and we're looking at states that have a larger urban areas versus rural urban areas, and we want to find and see if the proportion of autism in urban areas is less than the proportion of autism in rural areas. Assumed data were collected from a fairly urban state, and they found 182 8-year-olds had ASD out of 19,819. Assumed data was collected from a rural state, and they found 65 with ASD out of 2,696. Is there enough evidence to show that the proportion of children diagnosed with ASD in urban states is lower than the proportion in rural states? So the first part of the problem wants us to do a hypothesis test at the 4% level. So what they really mean here is the level of significance. Alpha is 4%. And the second part of the problem, they want us to compute a confidence interval for the difference in proportions, and they want a 92% confidence level. So for hypothesis testing, the acronym is PHANTOMS, P for parameter, H for hypothesis, A for the assumptions, N for the name of the test, T for the test statistic, O for obtain a p-value, M for make a decision, and S is state your conclusion. So there's a few more steps in hypothesis testing than for confidence interval. Confidence interval, we use panic, P for parameter, A for assumption, N for name of test, I for the interval, and C for a conclusion. Since the assumptions are going to be the same, we don't need to redo the assumptions to do a confidence interval, and since the parameter is again the same, we don't need to find or define the parameter again. So we only need to do the name of the test, the confidence interval, and a conclusion for part B that's different than part A. All right, the parameter, we have percentages or proportions of rural versus urban population of 8-year-olds with autism. So P1 parameter is proportion, and so I selected the notation for population proportion, and since there's two, one's going to be labeled P sub 1, and that one will be the proportion or percent of all 8-year-olds from a fairly urban state. And again, I selected that for the percentage of all, and here we're looking only at 8-year-olds from an urban state. The other parameter is going to be P2, and I selected P2. Notice in the selection there's a bunch of different either statistics or parameters. I didn't pick P hat, that's the statistic. The parameter is P2, the population proportion for rural. Okay, and we're looking for the percentage or proportion of all 8-year-olds from rural states. So that's what I selected there. So the null hypothesis is always going to have the equal symbol in it. And here the null hypothesis is assuming that the two population proportions are the same. That's the same as the difference is 0. So I selected P1 minus P2. And then if they're the same value, their difference should be 0. Notice it's always got an equal. In the above statement, it wanted us to test if it's lower, is urban lower than rural. So P1 minus 2, if P1 is less than P2, their difference should be less than 0. So the keyword is lower, and so I have a less than symbol in my alternative hypothesis. Since these 8-year-olds will either have autism or not have autism, that's a classification, a name or label. This is definitely qualitative data. So I selected qualitative versus quantitative. Since I have two different samples, I have double the conditions, but they're of course similar conditions. I want the number of successes to be bigger than or equal to 10 for both the urban and the rural data sets. I also want the number of failures. So that's sample size minus successes is going to be the number of failures. I want those to be bigger than 10 as well. Sample size minus the number of successes will be the number of failures. I want that to be bigger than or equal to 10. I also want 20 times the sample size to be less than or equal to the population size in both samples. And I want to have independent samples. Well, we do need to check these numerically. In the problem it said 182 from urban states had autism, and so that's definitely bigger than or equal to 10. It said 65 8-year-olds from rural state had autism, so that's bigger than or equal to 10. How did I get the number of failures? I took the sample size minus the number of successes, and so in the above paragraph we had 19,819 in the first sample, and I subtracted 182 from it and I got 19,637. For the number of failures in the second sample, I took the sample size 2 and subtracted 65, and the second sample size was 2,696 minus 65 with autism will be the number without autism. And that's how I arrived at 2,631. Again, both of these numbers are bigger than or equal to 10. Since it did not give me the population of the urban and the rural states, I assume it's very, very large, such that each population is greater than or equal to 20 times the sample size in each of the two samples. The name of the test is two-proportion z-test. There's a bunch of different options, but I have two proportions. It's a two-proportion z-test. The test statistic is going to be the difference. Well, the test statistic's down here, but the actual random variable is the difference in the two proportions, p1 hat minus p2 hat. And this is where I'm going to jump to the calculator to show us how I got this. So I'm going to bring up the calculator. And I did mention that the name of the test, so I'll go to Stat, Tests, 2-prop z-test, and we had 182 out of 19,819, and we had 65 out of 2,696. And my alternative hypothesis had a less than symbol in it. Sample size 1, number of successes. Sample size 2, number of successes. The alternative hypothesis had a less than symbol. Now I'm going to calculate. Okay. Just make sure I copied all the numbers in correctly. $65, $26.96. Make sure I entered these values incorrectly. 182 out of 19,819, 65 out of 2,696. We want less than. Okay, so that's all correct. Okay, so now I need to compute, sorry I scrolled too far down, P1 hat minus P2 hat. Unfortunately, it does not give me the difference here. So I'm going to copy that really quick here. And let's see if I can do a copy of that. Alright, so I'll do a new copy. Copy this, move this over to the sides. And I'm going to subtract P1 hat minus P2 hat. But as soon as I try to do this, I'll try to put 0. It just erases the screen. So I've copied it over here. 0.009 18.3. I'll just put quite a few decimals here. Maybe one more decimal. There's P1 hat minus P2 hat, and 0.02, 4109, and maybe 79. Do that subtraction. I've got plenty of decimals. To 4 decimals, it's negative 0.0149. So now, that's how I arrived at negative 0.0149. I subtracted the two sample proportions P1 hat and P2 hat. Unfortunately, you can't do this on your calculator screen and at the same time that you keep the image up there. So you might want to write these down separately and then do the calculation on your calculator. The next thing is to find the pooled proportion. It's the number of successes in both of them divided by the size of the samples in both. So 182 plus 65 divided by 19,819 plus 2,696. Now, your calculator does simplify that nicely. And here's the reduced fraction. Again, if you want to see this on the calculator, I'll type this up here. I've got 182 plus 65 divided by, and notice I'm putting parentheses over the entries in the numerator and parentheses over the entries in the denominator. So 19,819 plus 2,696. Hitting enter, I get a decimal, but if I hit math and then enter, it will reduce that to a fraction of 13/11/85. And that's how I arrived at that. So P1 hat minus P2 hat, that was the negative 0.0149. The P hat we just computed as 13 divided by 11/85. So P1 hat minus P2 hat, here's P1 hat, here's P2 hat. I just left them as fractions. P1 hat is 13/11/85. 1 minus P hat is, well, 1 minus 13/11/85. 1 over the sample size for the first one is 1 divided by 19,018. 1 divided by the second sample size is 1 divided by 2696. All those entries are input in to find the test statistic. Now I'm not going to do this on the calculator. I'm just going to rely again on using the test. So 2 prop z test. Once you hit calculate, it gives me the z-score, negative 6.98 to 2 decimals, and that's right here. The p-value, this is 1.47 times 10 to the minus 12. That means it's 0.0000, well, actually there's 11 zeros and then a 1. That's for all practical purposes, well, at least a 4 decimal place is 0. Since our p-value, which is to 4 decimal places is 0 is less than or equal to the level of significance, which was 4%, we reject the null hypothesis. So there's different options here. Of course, I selected reject the null hypothesis. There is significant, so it's either is or is not, but since the p-value is small, how small? Less than or equal to our level of significance. There is significant evidence to conclude that the percentage of all 8-year-olds from a fairly urban state with ASD is less than the percentage of all 8-year-olds from a fairly rural state. So notice there are several options. Because a hypothesis test is about a population, you do need to look for the words all in these statements. The percentage of all 8-year-olds from urban is less than the percentage of all 8-year-olds from rural. And that concludes the first part of the question. The second part of the question is for the confidence interval, but again, we already identified the parameter and the assumptions were satisfied. The name of the test for a confidence interval is 2-prop Z interval. And the question asks to compute a 92% confidence interval. And it's for the difference in the proportions, P1 minus P2. And if we go to the calculator, stat, tests, 2-prop Z int, and I do believe I have to scroll down a ways. There it is. Now, since I've already used 2-prop Z test, this information is still in the calculator. 182 from urban state had autism out of 19,819 sampled 8-year-olds. 65 students from a rural state out of 2,696 8-year-olds had autism. And we do want to change this to 92% because that's what the problem asked for. So here's the lower value for the confidence interval. Here's the upper value. And that's how I got, let me make this a little bit larger. Minus 0.02, minus 0.02 to minus 0.01. And they wanted this only to 3 decimal places. So to 1, 2, third decimal place is a 0. 1, 2, 3, that's a 9. Go to the right, that's bigger than or equal to 5, so I convert the 9 to a 10, so it's going to be 0.01. So that is how I got minus 0.02 to minus 0.10. That's the confidence interval. So we are 92% confident that the percentage of all 8-year-olds from a fairly urban state that are diagnosed with autism is between 1 and 2% less than. How to get 1? Because I converted this to a percent. How did I get 2? I converted this to a percent. Because they're both negative, I use the word less. So between 1 and 2% less. So the percentage of all 8-year-olds from a fairly urban state that are diagnosed with ASD is between 1 and 2% less than the percentage of all from a fairly rural. And that concludes this question for 2 sample proportions.